Hello students, welcome to this session. It's on electrostatic potential. What are the subtopics? Electric potential energy and electric potential. Relation between potential difference and electric field. Potential energy of a system of charges. Electric potential due to a point charge and multiple charges. And the last part is electric potential due to an electric dipole. What is electric potential energy? If a system consists of a large number of charges, what is the potential energy of the system? It is the work done in bringing the charges from infinity to their respective positions. Let's find an expression for change in electric potential energy, then to change in electric potential, then electric potential. Okay. So when a test charge is placed in an electric field, it experiences a force. Force is equal to F is equal to Q naught E. Now due to this electric field, to move the charge from one point to another point, some work is done. Now what is the work done by the external agent to move the charge from one point to the another point? It is against the field. So it is equal to the negative of the work done by the electric field. Okay, let's consider one example. You see, this is the surface of the earth. The gravitational field is there at every point here and near the surface of the earth it is extended. To move an object from this position A to a position B, some work is done. That work is done by the external agent. It is stored as gravitational potential energy. At every point in the gravitational field, the object has some gravitational potential energy and it can be obtained by getting the expression for work done. Similarly, in an electric field, at each point, if a charge is put, then the charge has some electrostatic potential energy. Thus, if the test charge is moved in the field by some external agent, then the work done by the external agent is the negative of the work done by the field. Now to get electric potential energy, let's consider some displacement ds. Now work done due to the electric field to move the charge through displacement ds, it is equal to F dot ds, it is Q naught E dot ds. Now what is the work done by the external agent? It is equal to minus Q naught dot ds. This is the change in potential energy. Okay, del U the change in potential energy. As this work is done by the field, the potential energy of the charge field system is changed by del U. It is equal to minus Q naught E dot ds. This is the work done by the electric field. Now this minus Q naught E dot ds, it is the change in electrostatic potential energy which is equal to the work done by the external agent. Work done by the external agent is nothing but the change in potential energy. Now, what is the potential then? Can you find the potential? It is equal to, so this is the change in potential energy. Now what is electric potential? The electric potential energy per unit charge. U by Q naught is the electric potential. Or what is change in potential? Del V. Del V is equal to del U by Q naught. Change in potential is equal to del U by Q naught. Del U is equal to, minus Q naught integration E dot ds. Now dividing by Q naught, it is equal to minus A to B E naught ds. So this is the change in potential. So change in potential is nothing but it is the work done in moving the charge from position A to position B, moving unit positive charge, from one position to another position, and it can be obtained by negative of the work done by the electric field. Now what is potential, electric potential at a point? So electric potential, energy per unit charge is electric potential. Now you want to find the electric potential at a point. What to do? So electric potential at a point is the work done to move unit positive charge from infinity to that point without any acceleration. You consider charge Q naught. Charge Q. This is the source charge, and the electric field is there around this charge everywhere. From the charge Q at a distance r, you want to find what is the potential due to this charge Q. Now, how can you find the expression for this potential at a distance r? It is the work done to bring unit positive charge from infinity to this point r. Basically, it is the change in the potential, or potential at point r minus potential at infinity is equal to minus integration of E dot dr. Since potential at infinity is taken as 0, so you can say it is the potential at point r. Okay, so it is equal to W by Q naught. It is a potential at a distance r from a point charge can be obtained. It is equal to KQ by r. If the source charge is small q, then at a distance r from it, the electrostatic potential V is equal to KQ by r. It can be obtained from the change in potential, and potential at infinity is taken as 0. Now, one important point is potential due to a point charge at a distance r is KQ by r, which is a scalar quantity, because W by Q naught, V is equal to W by Q naught. W is a scalar, so potential is a scalar quantity, or energy is a scalar quantity. Due to positive charge, V is positive, and due to negative charge, V is negative. Okay, what is its unit? It is equal to V is equal to W by Q naught. V is so it is, or you can say it is equal to U by Q naught, potential energy per unit charge. It is joule by coulomb. It is taken as volt. So its unit is volt in SI. 1 volt is equal to 1 joule by 1 coulomb. Here is one important statement. Potential is the characteristics of the electric field only, whereas potential energy is the characteristics of the charge field system. If a charge is placed in an electric field, it has some potential energy. Okay. Work and electric potential. If you know the difference of potential between 2 points, then what is the work done to move a charge from point A to point B? The potential difference is equal to del V. If you know the potential difference, then work done to move the charge from one position to other position where the potential difference is del V, it is equal to change in potential energy, which is equal to the charge value into change in potential. So W is equal to Q into del V. Okay. Electron volt is the amount of energy acquired by an electronic charge moving through a potential difference of 1 volt. 1 eV is equal to 1 E into 1 volt, that is equal to 1.6 into 10 to the power minus 19 coulomb into 1 volt, which is equal to 1.6 into 10 to the power minus 19 joule. So 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. This is the unit of energy in which the energy of electron can be expressed. Next, let's find what is the potential difference, relation between potential difference and electric field. This expression is already known to you. It is Vv minus Va is equal to del V. It is minus integration of E dot ds. And if E is constant, it can be taken outside, and integration of ds is equal to d. So Vv minus Va is equal to minus Ed. It is what the negative sign indicates here. The negative side indicates along the electric field line potential decreases. Let's consider this is the direction of the electric field or the electric field line. Now, if we will consider 2 points A and B here, 2 points A and B, the potential at point B is less than the potential at point A. Potential at point B is less than potential at point A, VA greater than VB. That is the significance. Now, if electric field is along x-axis, then you can find it is finding if from we will assume that the electric field is along x-axis, it is dV is equal to minus Ex dx, or Ex is minus dV by dx. Similarly, you can write the y component, it is minus dV by dy, and Ez is equal to minus dV by dz. In general, you can write E is equal to minus dV by dr. This dV by dr is called potential gradient. It is the rate of change of potential with distance in a particular direction. So, electric field is the negative of the potential gradient. This is the relation between electric field and potential difference. Now, let's find the electric potential energy of multiple charges. Consider two charges Q1, Q2 here. What is the potential energy of the system? It is equal to K Q1, Q2 by R12. Similarly, for the potential energy of a three-charge system, it is the potential energy Q1, Q2 by R12 plus K Q1, Q2, Q1, Q3 by R13 plus K Q2, Q3 by R23. Okay, so this is the potential energy of a three-charge system. Similarly, you can find the potential energy of a system where four charges are present. You will get 6 terms in that case. Now, electric potential due to multiple charges. You know what is the potential due to a point charge. Due to point charge Q at a distance R, what is the potential? KQ by R. Okay. For example, Q1 and Q2, two charges are present here. Then potential due to Q1 at this point, then potential due to Q2 at this point, then the total potential at point P is equal to potential due to Q1 plus potential due to Q2. It is the algebraic sum since potential is a scalar quantity. Thus, the electric potential due to several charges is the sum of electric potential due to individual charge. This is the algebraic sum. It is summation K Qi Ri. The K is constant of electrostatics. It is 1 by 4 pi epsilon naught. Now, electric potential due to a dipole. Using that concept, let's find what is the electric potential due to an electric dipole. You know, a dipole consists of two charges of equal magnitude and opposite sign separated by some distance. Let's consider a dipole along x-axis. Here, the potential at any point is the algebraic sum of the potential due to the individual charges. Here, let's consider a point R on the axis of the dipole. This point R, you want to find the potential here. So, let's find the potential due to minus Q charge and potential due to plus Q charge separately and have the algebraic sum. So, potential due to minus Q charge is equal to minus KQ by the distance, it is x minus a. Similarly, potential due to plus Q charge is equal to KQ by x plus a. This total distance. R is at a distance x from the midpoint. The length of the dipole is 2a. This distance is equal to a. So, the distance from plus Q charge is equal to x plus a. Similarly, the distance from minus Q charge is equal to x minus a. So, separately, let's find the potential due to minus Q charge and potential due to plus Q charge and to add them. Thus, here is equal to k minus q by x minus a plus q by x plus a, and taking the LCM and solving it, it is minus k 2aq by x square minus a square. Putting the value of 2aq is equal to p dipole moment. 2aq is equal to p the dipole moment. The value you can put here. it is minus kp by x square minus a square. If the point r is taken on this side, let it be r dash, then you will get potential at point r dash is equal to k p by x square minus a square. In that case, you will get plus. Thus, in general, V at point R is equal to plus minus Kp by x square minus a square. So, this is the electric potential at any point on the axial position. Okay. Similarly, what is the electric potential at any point on the equatorial position? Let's consider a point P on the equatorial line. To find the electric potential at point P due to the dipole, let's find electric potential due to minus q and plus q separately. Due to minus q charge, the electric potential at point P is equal to minus kq by r. This distance is equal to r. Due to plus q charge, it is kq by r plus. Thus, the total potential at point P is equal to potential due to minus q charge plus potential due to plus q charge, and the values are same and of opposite sign. So, what is the total potential? It is equal to 0. So, electric potential at any point P on the equatorial line is equal to 0, whereas electric field strength is non-zero. So, this is about the electric potential due to an electric dipole at axial position and equatorial position. Thus, in this video, we discussed about so many concepts. It's about electric potential energy, electric potential, then potential difference and electric field, what is the definition of electron volt. Then we discussed about potential energy of multiple charges, potential due to a system of charges. Then we discussed about electric potential due to an electric dipole at axial position and at equatorial position. Okay, thank you.